The question is to implement a try. That's it. No other way to do it. Just have to implement a try. So pretty much clear. We have to implement a try. So before implementing that, I just want to see like if everyone is familiar with try, or if they are not familiar, I will go a little bit of basic. Or if you are not familiar, you can just raise your hand so I can see like how many people are. Okay, I already got like get some overview. Okay, let's do a little bit of overview. So what is a trie? Trie is a tree-like data structure where the nodes of the tree, the entire alphabet or in the strings word can be retrieved by traversing down the branch of the tree. So basically there are a couple of things which are there in trie. You have a root, then root would have here you
भैया को भी लग रही है बदली
Okay, participants, if you are not participating, yes, just mute it. Thank you so much. Okay, cool. So trie is like a tree-like structure where you have a root and then it is followed by like 26 children and then you keep on adding. So basically if you have to add a Peter, so it would have a root, P will go there, then under P will put E, E will have T, then another E and ER. And if I have a pack, it would be similar. We already have a P. We don't do anything here. Then we go to E and then C and K. And we'll do for all the words. So can you think about a scenario where this kind of structure would be helpful? Like some kind of string matching data.
If you have some prefix and then we have to find all the numbers which match the prefix.
Yes.
Sorry, all the strings which match the prefix, like in a word dictionary.
Correct. But there are two things. If I have very few numbers or like few words, then I can even do it by going through each word. But these kind of things where we have massive words, like entire dictionary, like entire Oxford dictionary or something like that, where there are so huge, so many words, and if you see this kind of structure, so it tries to avoid duplicate. So if P and E, they are shared, then there will be only two nodes, P and D, and then followed by there would be their child. And if two words are same, then we can even avoid duplicates in the structure. The only thing is, this will take a huge amount of memory. If you see, every root will have 26 children, and then all of them will again have 26 children. To see how the massive tree would be formed. But if our dictionary is so big, the words are so big, large in number, then this structure is helpful while traversing or finding, searching, prefix, all other things would be helpful. For example, think in that way, how Google give you that recommendation when you type some word on Google, it will give you like auto, this thing.
Autocomplete.
Autocomplete. So basically they might be also running a try behind the scenes where your query will go, they'll try to get all kind of, for example, if you wrote PE on Google, it will go and see what all words can be found from PE, Peter, peck, packed, and other words. And then they do all other kind of logic also, some kind of a top or based on some priority geography, top search words. They do a lot of other, but the basic idea is like if you have a trie-like structure, you can do all sub prefix, even word matching and other things. I think this would be more clear if I if I show you a little bit snippet, how it looks like. So what a trie node would look like, I would have a map where we'll have a character, and again the value would be a trie node. And then I will also have a boolean like end of word. It will say, okay, this is the end of word. And then this is a constructor. And let's say I have to insert a word in the try. What I have to do? I will, so basically I will create a root, which will be try node. Then what I'm doing is I'll start crawling my tree. So first a crawl will be pointing to root, and I'll see if the first character of the word is there under my root or whatever current node I'm crawling. If it is there, well and good. Otherwise, if it is null, I will create a new node there and put that character there. And if once I'm doing that, whatever is the end last node which I've seen, I've marked that as end of word.
Okay, yeah.
So there's other way of doing this. If you don't want a map here, the other way of doing is taking a try, taking an array of try. We can, and then just, yeah. We know we are only dealing with 26 characters, and then I can just create like 26 here. So this would be like an array of try. So here we have given all 26 spaces as soon as we create a node. But if we take a map, we only allocate things when we need it. But there is always an argument between taking array versus map. As soon as you take array, there is less overhead of things. You know, it's a fixed memory and a couple of other things. I think we have discussed a couple of times between map and array.
Okay. So you said try node, right, as an array, or it is try? Okay.
Oh, sorry. It would be try node.
Try
My
node.
bad.
Okay. Oh, sorry, because the class name is also try, therefore, yeah.
Yeah. So this is a try node, and then the implementation in the class try.
Right.
Yeah. Thank you. So yeah. So there are two different ways. You can even go with the array or go with the map, whatever you feel like is okay. For example, we are talking about the try is case insensitive. So we can take a array 26 length. If it's case sensitive, then we have to make a double of size, and then we can even take a map there.
But here the try node for the array will be okay because we are dealing only with the lowercase characters. But if you have to deal with all of the characters, then I think the map should work fine, right?
Yes.
Okay.
What if you have to print like all the words in the dictionary in a alphabetical order?
Yes, that could also be doable.
Okay, then array makes more sense because hash are not ordered.
Yeah, but it depends how we are doing a hash. We can do it like a what is that?
You can use a tree map, but that's what, like, it depends upon the question.
Yeah.
Both choices are like equally good. It depends like what scenario you are trying to solve.
Yes.
Oh, so it means we need to be very careful whether to choose an array or a map. So we need to understand the requirement. Okay, got it. Yeah, thank you.
So,
I mean, generally we take array when we know the side up front.
Yeah. Based on the requirement.
Yeah.
If there is a chance that requirement may change, then changing this structure would be like changing the entire try implementation. So we have to be really thoughtful while asking the requirements. So if the person says tomorrow right now I only care about lowercase, but tomorrow the uppercase can come, that means I have to restructure my entire tree or something like that. So could be expected to ask all the clarifying questions. So let's try ourselves first and then see how it goes. Okay, let's do that. Okay. Can you see the whiteboard?
Yes.
Okay, let's try to, with all this theoretical things which you just saw, what we have seen, let's try to try now. And I can't get all the controls. Okay, got it. I'm just setting up my whiteboard. Oops. What is happening? Oh, I can't pick up eraser. Sorry, something is going weird with my whiteboard. Wait, I will
Do you want me to make?
You can use the like Leetcode. If you
I want to draw. That's right. Let
Okay.
me.
We can see it now.
Yeah. Okay. Yeah, I think this is better. Something crazy happened last time. Okay. So based on this understanding, what is happening? Okay. Based on this understanding, we'll have something like a root. Right now, our try is empty. I'm going to insert an apple there. What am I supposed to do?
So if it is a root, actually, if you are using an array, I'm assuming that.
Mm-hmm.
So I need to go to the A character index,
Which is 0.
which is 0, yeah. And then at that index, I need to actually create another try node and assign it.
Oh, yeah. And then it would be A here. This would be a try node, but which will be denoting to A. So basically from roots array, I would say like this is A and this is actually a try node.
Yeah.
And from there, I will go to P and another P and then L and E. For example, now I'm inserting this app. I'll go root, A is there, P is already there, P is there, so I don't need to do anything. But I have to also mark that as end of my word.
Mm-hmm.
This is my end of word. In the same way, I can insert a lot of things. So if I have to search something, so search and starts with a little different. I'll start with the apple. I'll say, oh, A is there, P is there, P is there, L is there, E is there. And then that node should be also end of word. If that is not end of word, then it is not a search. But if it is start with, then we don't care about the end of word.
Oh, okay.
So let's see a little bit of the solution. And then let's say we're meeting controls. Okay, so let's see a little bit of solution here. Okay, so we have to implement these methods: insert, search, and starts with. So if you see, I have created a try node, which is again a map of children, end of word, and that's all I'll initialize the hash map when the node is created for the first time and set the end of word false. And then when I have to do an insert, what I'm doing is I'm just making crawl as root, taking the first character, seeing if it is there in the root or not. If it is not, then create a new try node, put it that character in the root and that node as its value, and then make that crawl as the current node. So keep on crawling. In the previous example, now we are at this node. If we are inserting apple, we are now, so now crawl is pointing to a try node. Okay. and root would have this a as its in its children. Now next thing, and our word was now we get p. P is also not under a, so we'll just create that under a, and now my crawl is pointing to p. Then similar another p will come, then L will come, and E will come, and then the word is over. And then we set that E is my end of word. And then again I got APP. I already have, then again I'll start with the root. I already have A here, able to fetch A, because you remember if I just created, and then just point this to A. Then P will come, then another P will come, and in this case we have not created any new try node. And in the same way, I will set that P as my end of word. Now let's say I got another word like APC. A would be here under the root. Now it will point to A. Then P will be also there under A. When C will come, it's not there. So we'll create a new node here, put it under P, and then this guy will point to C. And we are done with the word, and then we'll set this end of word as true for at C. Is that clear?
Yeah, the insert is clear. Yeah.
Okay. So if that is clear, then even the search would be same thing. Now, let's say I want to search a word. So right now, what we have inserted in our try, we have inserted this apple and A, B, C. Let's say I'm going to search something like A, B, C. Then I will start with this. At the root, I have A, so that is good. If I couldn't find A at my root, immediately I can return false, because no, I can't go further. Then now my crawl is pointing to A. Then under A, we don't have any B. So that means I can return immediately false. Correct?
Yeah.
Yeah.
So now let's say we are searching a word APPL. So first A will come, under A will get P, under P will get another P, then we'll get L. Word is done, but L does not donate to end of word. So I can't say that APPL was there in my try. So I have to return false. But say if I was having apple, then L would have E. We are going one more character, and then here it will say end of word. So that is good. So we can return true there. And let's say we are doing something here where we are looking for a starts with. So we got a word like apple or A, B, C. First we look for first we look for A, which is there. Then I look for B, which is not there. That means such kind of prefix cannot be possible. So I have to return false here. Then let's say I have A, P, P, L. I was having A, under A I got P, and under P again I got P, then under P I got L, word is done, and then when we are out, we can just return true. So the difference is over here between starts with or search. Here you look for, in the start, in the search you look for end of word is true or not. Here we just look for true. Like we just return true, we are done with word, it is a prefix, we are good to go. So is it clear, or you want me to spend more time on this?
So go ahead. Yeah, sorry.
Yes. I have a question.
Yeah.
What if the postfix is required to search? Does it mean we need another try, or we can put prefix search and postfix in one try? Yeah, I have that question in an interview. Yeah.
So means like you want to search something like, let's take example. You got something to, so in our try I have these three words. So you want to search something like LE.
Mm-hmm. Yeah.
Like, okay, so what I think is what we can do is so basically try is again a tree. You can do a depth first search or a breadth first search over here, but it seems like in your requirement you want to do something like you want to traverse entire try and find if there is a path till leaf where you can find this pattern.
Yeah, that's the all of n search, but the requirement is how to do the postfix search, like the prefix search here.
So some other ways which I think we can do is like with every node, you can keep like how every node you can keep whatever the postfix part is left. Did you get that? So that will be additional memory, but every character or every try node will also can have, let's say, now I'm just throwing some ideas. Even I don't know how much.
Can we reverse the word and do the build another try? I mean, if you reverse a word and then or not reverse it, but build a try from right to left, and then that could help to do the postfix, wouldn't it?
No, so you're telling inserting that word, inserting the reverse word in that try?
Yes. So E first, like for Apple, you know, instead of APPLE, we will do ELPPA.
But the trick is, okay, Marcos, is it Emily?
Yes, yeah.
Yeah, Emily, I think another clarification part is, do I need to implement both start and prefix and postfix?
Yeah, it's not specific requirement. I know it's just general asking how to do the prefix search and postfix search in a trie. My solution is to build two trie. One is like you in your code, it's a prefix search trie. And we can build another trie by using the reverse the word apple and build the trie from the end to the first index. Yeah, that's my solution, but I'm not sure it's a correct answer. So,
other way is that though it will take too much memory, we can insert all the prefix in the trie.
So like that's a valid answer. I believe like we can create like two tries, one with the forward going words and one with the reverse going words. Okay, and that would work. Like from an interview point of perspective, that would work. The other approach that we can take is to build a suffix tree. It's a like different data structure, but built on top of trie, which solves this particular problem for finding the suffixes. It's called suffix tree. And there is an interesting, like read about the suffix tree. But from the interview point of perspective, if you can come up with creating two tries, one with the forward word and one with the reverse word, it should be, I believe, like more than sufficient. Read about the suffix tree, and there is also interesting algorithm called Equinox Algorithm, using which like you can create a suffix tree in linear time. So just there is something called suffix tree too for this approach.
Yeah. Yeah. Thank you.
Gaurav, can you pass put that algorithm name in the chat so people can copy that?
Sure.
Thank you. Okay, I think that was an interesting situation. We all might can get that in a real interview. So yeah, I think a fair answer to get started. But if somebody is still asking more better thing, then some theoretical answers like Suffix Tree could be a savior. Okay, I think that's it from my